part in your work energy and power is the conservation of energy. So the first thing we want to talk about is, what does it mean if something is conserved? If something is conserved, that means that it's going to remain constant, right? So you totally transfer something from one side to another side. And while you do that, you will see that the original equation is going to be equal to the final equation, that kind of a thing. Initial equals final is what we would look at. So for instance, I have a light bulb, I break the light bulb. If I scoop up all the pieces of just the light bulb and I take the mass of it, then that should equal the mass of the light bulb prior to it breaking. So a broken bulb will have the same mass as a new light bulb as long as all the pieces are gathered up. So there's the conservation of mass. In other words, what you start with equals what you ended with. So as long as you're just picking up glass. Okay, so next thing, mechanical energy. When we talk about mechanical energy, we're talking about a combination of two different forms of energy. And that is going to be your potential energy and your kinetic energy. Remember, you have two different forms of potential. You can either have GPE and or EPE, and then your kinetic's only one form. So the equation that we want to look at here is that you're going to have your mechanical energy is going to equal your PE, whatever form it is, and your KE energy. When you talk about the conservation of mechanical energy, you want to say MEI, the initial mechanical energy, equals the final mechanical energy. To break that down a little bit further, that would mean that you would have PEI, once again, be specific on the flavor of PEI, plus KEI equals PEF, be specific, plus KEF. This equation is good to use only in the absence of what, guys? What's going to come in here and completely change your answers around? How come sometimes all of your kinetic energy is not transferred to potential energy? How come all of your potential energy is not usually transferred to your kinetic energy? Who's present that goofs this up? Friction is present, yeah, so it's only going to be able to say, or you are only going to be able to say that you do have complete transfer of mechanical energy in the absence of friction. Therefore, energy is conserved in this equation, so the total mechanical energy remains constant. Whatever you started with is what you're going to end with. The word constant's underneath there. So total mechanical energy. Okay. So what if there is friction present in this system? The conservation of mechanical energy no longer exists. Why? Because it's not just a total transfer of PE to KE, vice versa, due to dissipation of energy. What are the three things that we see due to the dissipation of energy, guys? We see heat, we see light, and we have sound. So if those three things are present, then you do not have complete transfer of mechanical energy. Some of that energy has been dissipated, not lost. Please do not say the word lost. Stuff in science is not lost, nor is it created, nor is it destroyed, right? It just changes from one form to the next, i.e. dissipated. So energy conservation will occur when acceleration varies. Shape of the object. So the shape of the object has really not that much to do with the mechanical energy. It is the shape of the object that is a concern when it comes into friction. Like, think about air friction, like aerodynamics, right? Resistance of the air. If you work for one of the motor companies and you're one of the chief engineers in the designing department, you want to try to make this car as sleek as possible, right? So you want a lot of curves and turns in it. You don't really want a boxy kind of shape because it would be a lot harder for you to cut through the air while you're moving. That would definitely affect your gas mileage on your car. So that is something that you would want to take into consideration because, as you know, we do not live in a frictionless world. Also, the surface that you're riding on. On the picture that we have down here, we have two of the same, well, not the same, but close to, cars. One is on a track that has a bunch of traction on it. cement, blacktop, asphalt, and then the other one's on grass, which is definitely going to have a lower mu k value. So it's going to slide a lot more. Okay, in the presence of kinetic friction. So kinetic friction means that the object is in motion. So in the presence of kinetic friction, non-mechanical energy is no longer negligible. So we're going to have to refer to this as non-mechanical. So in other words, mechanical energy is no longer conserved because there is the presence of heat, light, sound. Okay, so this flow chart here, pretty cool. Two different forms of energy. You have mechanical energy and you have non-mechanical energy. Once again, if you have non-mechanical energy, you have heat, light, and sound that the energy is dissipated into. Your two different forms of mechanical energy are kinetic energy, which is Ke equals 1/2 mv squared. And you also have potential energy, which you can have two different forms of that. The first form that we'll uncover here is your gravitational potential energy, which is GPE equals mgh, in which h is the variable that you would want to have initial and final. And then the last one that we want to uncover is your elastic potential energy. That would be EPE equals 1/2 kx squared, where it is your displacement that you'd want to change, because your k, your spring constant, is constant. Just like in GPE, your g, acceleration due to gravity, is going to be constant. So looking at our sample problem here, reading through the problem, it says that the child starts from rest, so that's your initial velocity, 0 meters per second. Zooms down a slide, frictionless slide, starting at an initial height, so hi is 3.00 meters. What is her speed at the bottom of the slide, assuming that her mass is 25.0 kilograms? So at the bottom of the slide, so your final height is 0 meters, right? You're sliding down this, so you have a 9.81 meters per second squared, and you are trying to calculate your final velocity in meters per second. So you have your MEI equals MEF. Be more specific, guys. You have GPEI plus KEI equals GPEF plus KEF. You can break down this and totally get rid of your GPEF because your HF is equal to 0. Furthermore, you can get rid of KEI because your initial velocity is 0. So therefore, we have MGHI equals 1/2 MVF squared. You want to get VF all by itself, so to rearrange that, we're going to get the square root of 2GHI. It's going to equal VF. Well, what happened to M? The M's canceled out, right? Because you divided by 2 over M. Let me correct myself. You divide by 2 over M, so that would give you your 2 in your numerator, but an M in the numerator and an M in the denominator cancel themselves out. So plugging in our values here, we have 2 times 9.81 times 3.00. Please put that in your calculator, guys. 2 times 9.81 times 3.00. So that should give you a calculator answer of 7.672. Looking over at your givens, your least number of sig figs is 3 sig figs, in which the 2 does not round the 7 up. So you have 7.67 meters per second as your final velocity for this problem. And that wraps up our discussion on potential energy, on conservation of energy.